Hi, this is Mark Kemper with EMS. In this video we're going to demonstrate the new Creaform HandySCAN. It comes in a 700 and a 300 model. Now Creaform's been around for a long time and known for its handheld scanners. This new scanner is really a big advancement in their handheld scanning technology. The first thing you'll notice right away is just how small it is. You can see it's very narrow, it's very compact, lightweight, weighs just over a pound, very easy to handle and scan. So like most of their scanners, the way this one works is you've got two sensors here in the front, basically cameras, okay? And then here is where the lasers project out. Now this is one of the new and unique things about this new model, which we'll talk about here in the demo today. And then around the sensor you have some LED lights that light up the targets, which we'll show and talk about here shortly. This scanner, this is the whole unit here with a USB 3 cable, plugs into a compatible laptop or desktop computer with the Creaform VX Elements software, which is basically the capture software. So again, very lightweight, very portable. This is great when you have to get out in the field and get into tight areas, such as a vehicle or inside a big, industrial pump or a big housing or anything like that. It's laser based, so that works very well on shiny and dark things. Also what works in outdoor lights, direct sunlight. So that's very handy, or where you have parts that have varying color. Okay, and we've got some new buttons here on the back I'll talk about for handling situations like that. And again, very small and portable. Here's the case that it comes with. So you can see here it's very small. We can ship this overnight to all our different offices, for a reasonable price. I can get it shipped, overnight, and they can have it at the other office and get out in the field and start scanning. Or if we're going to go fly somewhere, I can check this into the overhead compartment on an aircraft versus having to check it as luggage. So again, very portable, very easy to use, as you're going to see here in the demo. Now with the HandySCAN scanner, it requires targets on the part in order to scan, okay? And a lot of times people think, oh, targets, I'm going to have to target the part, that's a lot of work. It's actually really easy on most things, and then there's some other tricks I'll show you. The advantage of targeting the part is it allows many things to happen. One, I can move the part around because the targets are on the part. It's going to be looking at the targets and allow it to allow the part to move around. The other thing is targets improve accuracy. Even scanners that don't require targets, most people end up using targets with them anyways because they'll improve accuracy. If you're just doing geometry-based alignment, which is basically take a scan, take another scan, line them up, there's more room for error in those alignment processes, and the more you scan, the more error you can get. Okay, so targets are really a good thing, and they come in different formats. This is an aluminum part, so I'm using sticky targets. Basically, they come in a box like this. They self-dispense. I just pull this down, grab a target out, and place it somewhere here on the part. Okay, and you need the targets on a small part like this about every 3 or 4 inches. On something bigger, flatter, you might get away with larger targets. But so we have the sticky targets, we have magnetic targets, and then we have other things we use. So sometimes we have a small part or maybe a tall, long, skinny part. I might fixture up some target bars, have the part in the middle, and have maybe 2 or 3 of these bars. And as long as the targets are in the line of sight, it'll pick up the part, the scanner will pick up the part shape while it's looking at the targets. So they can be around the part on something like this. Sometimes we'll just have a small part and set it on a table like this that has targets on it. The only disadvantage to this setup is once you set it here, since the targets aren't on the part, you can't move that part around, okay? So, but again, the advantage of targets is, in this case, I've got a part that I've got to scan both sides of it. You're going to see me be able to do that all really automatically, where if I was using, for example, let's say an ARM-based scanner, I would have to scan the part and then save that file, flip it over, and scan it again. The problem with ARM-based scanners is the part can't move while you're scanning. The base of the the arm can't move, and you need a real, rigid setup, almost like a CMM, in order to keep your accuracy, because otherwise you're going to have multiple setups. You got to calibrate. If you're doing large parts, you need to do a process called leapfrogging, and all of that just introduces error. With targets, it just makes it easy to scan. So about a minute to target a part like this, and you're going to see the payoff, which is how quick and easy we can scan. So how targets work is it's really a process called triangulation. So just like GPS, where you need to see 3 or 4 satellites in the sky, scanner does the same thing. It needs to see 3 or 4 targets, at least that. Most of the time it sees more than that, and that can track its position as we continuously scan around. Okay, so as we go around, as long as it can see those targets, it'll scan. If it can't, it'll stop scanning, go to a different spot. And you can see the targets are actually random here on the part. You want them to be random. If they were all symmetrical, it would actually get lost. And then you can see I've got my part on a stand here, just a couple little blocks, and that just keeps it off the table because we're going to end up picking up some of that scan data, and we don't want our part kind of stuck to that. Just for editing later, it just makes it really easy to get rid of that data. You'll see it as we go along. So the difference between the 700 and the 300 model is they really look the same. It's just a few differences. One is this has an accuracy of just over 1/1000th of an inch, where the 300 model is just over 1.5 thousandths. This has 7 laser lines, which is split, so it's actually 14 laser lines, which you'll see here in a minute, and the 300 has 6. And this also has a single line mode, which I'll show you in a minute. So a little faster scanning, a little better accuracy in the 700 model. But basically the way it works is there's a button on the back, and we literally just click the button once, and we start scanning. And you can see all the laser lines. And as I move around the part, you're going to see the targets will either be white or red. So as it acquires them, red it's using and white it basically knows about. So you can see how quickly I'm moving around this part. Okay? And we'll move up and down. Now we're going to get to an area here where it's bare metal. It's real shiny, okay? And it's actually doing a pretty good job. But at any time, I've got a couple different things I can control here, one of them being the shutter. And what that does is it slows down or speeds up. In this case, I want to slow down the shutter speed, and I want to increase the laser power. So when I have dark or shiny surfaces, I want to be able to do that. The downside is I've got to go a little bit slower because it can't capture the data as fast. But again, having this mode where I can turn it up and down just right as I'm moving along. So now I've already got that area. I'll crank it down a little bit, and then you can see me moving along. And like all scanners, it's line of sight. So as I move around, we want to definitely aim the scanner kind of perpendicular to the surface. That always gives us the best data. And again, having the freedom of the movement of my arm, it's very easy. You can see me, if I want to get, for example, this wall in there, I just crank that over. And you can see it picking that up. And you can basically see it picking up that flange or that lip, whatever you want to call it. Now the other thing this has is this single line mode. Okay? And what it does is it orients a single line perpendicular to the lenses. And this is really good to get into narrow cavities. Scanners are not only line of sight, but basically the sensor has to see the light source. So when you get to something narrow, they basically never converge. They never see each other. So by orienting it perpendicular to the cameras and just doing a single line that the cameras focus on, you can see I'm getting down in this narrow area, getting down in these. And again, just a click of a button and I go back. So I can adjust the shutter on the fly, I can zoom in and out on the fly, and I can go to that single line mode all without stopping scanning. But the beauty is I can start and stop anytime I want. So if I stop, have to do something, and let's say I forgot where I was, it doesn't matter. Okay, I jump back over here. You can see it automatically orients the data to that position. Okay, because again, the randomness of the target. So you can see I'm pretty much done. Probably doing more talking here than scanning, but just I go around. Now, once I'm done here, I need to get to the back side of the part, and again, this is where targets really work out well. So what I'm going to do is I'm going to lift the part up. I'm going to kind of hold it like this. I'm going to go back to a known spot, which in this case works out real well right here. And I'm just going to start slowly moving around. And what I'm going to do first is I'm just going to kind of scan it to grab the targets. Okay? And again, you can see the beauty, even though I'm sliding the part all around, it's still tracking everything. Okay? And again, I'm going to put my little stands back on the part here, and that's just to keep it up in the air. It just makes it easier later when we go to edit the data that I'm not connected to the table. Okay? So again, even though the part's kind of loose and falling around, doesn't matter. Now I can just keep rotating around and scanning. And you can kind of see all that table scatter data. That can be a real pain to clean up. But again, by just putting a few little stands underneath it, it keeps that data separated from our part data, so it makes it super easy. Okay? So again, it's so easy to move around. I can even have the part moving as I'm scanning, which is really unheard of in a lot of different scanners. Okay? So it's continuous scanning. We're capturing up to, in this scanner, 480,000 points per second on the 700 model and 206,000 on the 300 model. Okay? And again, I can go to that single line mode. I know it's probably hard to see up there because I've got all the scatter data. And you get that from the table. Some of the shiny areas are going to reflect some of the data, but it's just kind of out in space. And shortly here we'll go to the software and you'll see how easy that is to clean up. So I can go in that single line mode, and it's kind of like digital spray painting. I just keep working my way around the part. I don't have to worry about over scanning the part. It's not going to hurt anything. I'll show you in the software how it takes all this raw scan data and processes it, but I can get down in these holes. And again, anytime I want, I can go back to that 14 line mode. So it probably took me as long to target this part as it does to scan the part. Now, of course, I've been kind of talking as I'm scanning, but I could target this part in a minute and scan it in a minute, minute and a half, maybe 2 minutes at the most. And I can stop, I can look at the data, see some spots I missed, go back. Also, you got that the green bar, that just shows me if I'm too close or too far away. There's also a readout right here too, okay? So you can see I'm getting too close, it turns red. If I get too far away, it just shuts off. It'll just stop scanning when it can't acquire targets. I come back in. So it's pretty easy to use. You don't have to be a CAD expert to learn how to use this scanner. Some basic training, basic techniques, and you can go out and send really anybody out to do the scanning. So I just keep going along until I think I'm done, and then I'll stop and we'll process the scan data. Okay? And again, I could take the part if I thought maybe I missed a spot on the other side, or maybe I want to stand it up on end like this. And continue scanning. So it'll jump around. Again, because it's all line of sight, all scanners are line of sight, it makes it great to be able to just hit it at every angle to make sure I've got all my scan data. Okay? So that's really it. Very easy to use, very small, very portable. It's really getting the kind of metrology grade in a handheld. Very, very high accuracy. Just over 1/1000th of an inch was unheard of, not too long ago in a device like this. So very easy to use, small, portable, laser-based, which is good to do those dark and shiny surfaces as well as other types, all in a nice package. So what we'll do next is we'll go into the software, we'll actually look at the scan data, show you how to clean it up and get it ready for downstream applications like inspection or reverse engineering or some other process we may want to do.
Okay, so here we are now in the VX Elements software, and this is the capture software that comes with the scanner, and we can rotate the part around, we can look at it, we can do some basic things in here. You can see where our targets were on the part. Now when we're done and we process this data, it actually does curvature based hole filling where there's curvature on the part and flat where there's not. And we'll actually fill in where those targets are. So you'll see when we're done here, won't even notice where those targets were. So first thing I want to do is I want to do some basic cleanup in here before we take it to any downstream application. That'll just make it easier to work. And there's some nice tools in here to work right with the raw scan data. So I'll click on the scan button and show you a few things. So right now our resolution is set at 0.5 millimeters. Now underneath this polygon model, which are basically triangles, is raw points. All scanners just collect raw points. Now what you're seeing on the screen here is polygons, which are triangles, and we've set it to be 0.5 millimeters. You can set that up or down as need be. So if you had something more flat, you could make larger triangles, and if you had something with more detail to it, you'd want to make that smaller. Now resolution and accuracy are two separate things. the accuracy is really those, those points or those triangles. Resolution is really the fidelity. So even if I crank the size of the triangles up, theoretically it would still be accurate. The corners or the vertexes of those triangles would be accurate, but we'd start to lose fidelity of the part. So it's really the balance of resolution and accuracy that really gives you optimal results. So as we mentioned before, we've got this scatter data where we had the part on the table and then flipped it and scanned it again. One nice tool in here is remove isolated patches. So you see as I slide that along, it instantly gets rid of all that kind of data that's floating out in space. So when we scan, we really don't have to worry about that. We can also have it auto-fill in holes. You'll see some small areas we missed, especially in some of these shiny corners where we had those machine surfaces. For our reverse engineering, it's not critical. We have every completely watertight model. As long as we have most of it, we'll be just fine. And you can see the quality of the data. You can easily read that serial number on the part or part number. You can even see the roughness of the casting. You can see here where there were some blemishes and some different things. So very good quality, very clean data. And then we can also optimize the scan mesh. I'll slide that one up a little bit. Boundary organization, that just sharpens up the boundaries. We can also decimate. I'll leave that turned off. So once we get all these settings the way we want, and if you notice we're at about 3.3 million triangles right now, let's go ahead and hit apply. And what it's going to do now is go back to that raw underlying point cloud, optimize the mesh a little bit, just kind of clean it up, any kind of points that are still maybe floating out a little bit, sharpen up the edges, fill in some of the holes, including where the targets were, and permanently remove those isolated patches. So this will take a few minutes to do, but once this is done, we're going to have a nice clean model. For time purposes, we went ahead and paused the video. But you can see now here it's really cleaned up the model nice and gotten rid of all that data, and you can see our polygon count has dropped down a little bit. So next thing we're going to do is just come in here and we're going to say export and export the mesh, and we'll just overwrite this file here, and basically it's going to stick it out as a polygon mesh, and that can go out in formats like STL, Ply, Vermal, and many others. And really what we're trying to do is take it to a downstream application such as VX Model, which has some basic editing and auto surfacing. That's another product from Creaform. Or in this case, I'm in Design X, which is a full-blown feature-based solid modeling and surface modeling product that can bring in scan data and work with it. Because most CAD systems can't really do much with scan data. They can bring it in and look at it, but it's a huge polygon file, and they can't do much else with it typically. So here we are in Design X, and let's take a closer look. And I'm going to turn on the edges of the triangle. So if I zoom out, you can see it just looks like a blob. But when I zoom in, you can actually see that 0.5 millimeter nice even spacing of those triangles across that whole part. So that's basically what this is. And let's just go back to our shaded view. Okay. So then from here, what we're going to do is typically set this up in a coordinate system and then start modeling it. Now in this demo we're not going to do that, but basically the end result would be this. This is a feature-based solid model of that part from that scan data. And really how that's done is if we go over here and look, this is history tree modeling, just like you would see in a SolidWorks, a Pro Engineer, a Siemens, an Inventor, and others. And if you roll all the way through, you can see there's about 70 features and 30 or 40 fillets and chamfers and other things. So this actually took about a day, probably day and a half, to build this CAD model from that scan data. It's not an automatic process whatsoever if you want a feature-based model. You could do a quick auto surface, but that's not going to give you features. That's not going to give you planes and cylinders and things like that. So this is what we really want. Again, how that works is if we just come in here and take a look at the first sketch and start to walk through the history tree, you can see it's just like a CAD model. So basically we extract sketches from the scan data, we define those sketches, add parametrics, dimensions, just like you would do in a CAD system, and then we extrude or we revolve, or we may make a series of sections and then loft and so forth. So it's still a pretty involved process all the way through the model. Now, it's definitely more accurate and faster than if you tried to do this manually. If you had to manually measure this and do it, it would certainly take you a lot longer, and it wouldn't be very accurate. This is definitely the best way to go. Now, if we turn the scan data back on, you'll notice there's differences between the scan data and the CAD data. As we're modeling this, one of the things we're going to do is turn on what we call our accuracy analyzer. And what that's going to do is that's going to compare the raw scan data to the CAD data. And if you look over here, we're in inches now, where basically everything in green is within 0.004 of an inch. Everything headed towards red is in the positive direction, out of tolerance, and blue is in the negative direction. So when we reverse engineer, we're going to take and scan a manufactured part which is imperfect, and we want to redesign it or re-engineer it back to a perfect CAD model. So you can see when we do that, we're going to see inaccuracies or differences in the CAD model compared to the scan data. So for example, this flange here at the top was certainly designed flat, but when we scanned it, it wasn't flat. So we made it flat in the CAD model, and you can see about 3/4 of it is flat or within that tolerance. But down on this end, you can see it's out, as I highlight over different areas of it, as much as about 7 or 8 thousandths of an inch. So we certainly don't want to design a CAD model with that inaccuracy in it, so we'll make it flat, and you're seeing the difference there. Let's roll over and look at the bottom and look at this main flange. Again, same thing. Part of it is in spec and a lot of it isn't. But again, when we reverse engineer it, we're probably going to want to make that flat. Now, other areas of the part over in here, these kind of near net areas, they don't have to be perfect. We're not too worried about those. But certainly hole locations, flat areas, we definitely want to try to either average that deviation or review with the customer and try to determine how they want some of this stuff modeled. But typically we're going to want to reverse engineer this back to the perfect CAD model. So again, as we're designing this, we can look at those differences and make judgment calls on what we want to do. So let's turn that off and turn off the CAD model and just look at this again. So again, what we did here is we took this raw scan data, basically feature by feature, cutting sections through the data, building those sketches, and then extruding, lofting, and so forth. And we have other videos that go into a lot more detail in the actual CAD modeling process. Now the other thing we can do is once we're done is we could generate, for example, a rendering from that CAD model or an animation, as you see here. So that's always a nice deliverable for the customer. And then finally, what we're typically going to do is we're going to take this CAD model and we are either going to export it as a CAD file, and we can go into neutral formats such as IGES, STEP, Parasolid, ASICS, and a few others, or in DesignX is a thing called Live Transfer. And what that will do is that will actually transfer the file to SolidWorks, to Siemens, Creo or Pro E, AutoCAD, Inventor, and Solid Edge. And how that works is you have to have that host CAD system, and it'll roll back the history tree, it'll open up the CAD software, and it'll literally rebuild each one of these features in that host system. It'll build planes, it'll build sketches, it'll do extrusions, everything. The advantage of that over a neutral file is then you have the history tree. So if you were going to do further editings to this file or make changes to this part, it would be easier to do having those sketches, having those individual features. Now, the live transfer isn't perfect, and it depends on the CAD system, but anywhere from 50% to about 85% of all the features and sketches go through automatically. And the things that it can't solve, you usually have to go in and do some manual intervention in the CAD system and then let it continue doing the transfer. But it's a very powerful tool to get a native CAD file when it's required. So just to kind of wrap up this video, we took the Creaform HandySCAN 700. We 3D scanned this part literally in a matter of minutes after putting on some targets. And then we cleaned up the data a little bit in VX Elements, brought it here, in this case in DesignX, where we reverse engineered it into a feature-based solid model, and then we're either exporting it out in a neutral format like IGES or STEP, or using that live transfer to get a native file. So that concludes this demonstration.